I need to solve systems of equations like this one. So this is representative of an equation. A times x equals b, which we solve by inverting A, where A is a matrix and x and b are vectors. The simplest possible system is just two equations like this. We have an x vector defining two variables that we are searching for, solving for, and two equations that this equals one of the x vectors, or x scalars in this case, plus the other, and the other equation is just the same but with a minus sign. So this is a solvable system of equations, but we need the matrix to solve it, A. We need A here to be able to inverse it or make another type of solver. So getting the equation is rather simple, and you can do it by hand, and it looks like this. What? I have a lot of equations down here. Sorry. That was not the simplest equation. So back to it. I have an x vector also. Professional YouTuber. Now we have the matrix. The matrix contains, says down here in my solver, 1, 1, 1, minus 1. And as you can see, the matrix just contains the coefficients of the system of equations. You see the 1, 1, 1 are these ones. You have a 1 here, 1 here. I know my cursor is probably not showing because of OBS is not really working. And also ignore the red squiggly lines, because this is my own language used in this file, but Visual Studio interpret this as a C++ file because I want to be able to use the hotkeys for comment. So the red lines are to be ignored. Anyway, in this system of equations, if you can see my cursor, I move it around above that now. Anyway, we can see we have 4 x variables on this side, and those 4 variables are these 4 numbers, these 4 coefficients in the matrix. So if I were to do this, I put 2 times that there and 3 times that there. You will see in the matrix we have a 2 and a minus 3. So now we can see how the matrix is constructed. And on the other side we have variables called B11a and B11b, and they show up in the B vector down here, and the X vector also is described down here. So this is all the things we need to solve the system of equations in a solver. Simple. You could do this by hand, but when you have about 100 equations or so, it's not that easy. I have made a matrix of 70 equations by hand. It's very tedious and very error prone, and I am not doing that again. So I have made a matrix compiler that takes my equations in any form I see fit, that is easy to read and debug and produce, and then it automatically makes the matrix for me. Very sweet. So this was the explanation of how a system of equation works and what we need to do. So we need the matrix from this type of equations up here that you can read. Okay. These names are now X11. They should be named front wheel, rear engine, torque, mass, velocity, temperature or something that you can read, but this is just anything now, so I didn't want to give them two interpretable names. But I'm sure you get the picture. If we had real variable names up here, these equations would really mean something like F equals m times A, or the temperature is something with heat capacity this and heat capacity that. So I am now solving this very simple system of equations, or I'm getting the matrix so I can give the matrix to another solver. Anyway, this can do a lot more advanced things than that, and it also helps me to not make mistakes because I have a lot of error messages when I mess up. And I will make another video separately on error messages. But the first thing we have to do, this is just a small readme file about what the syntax is for the language I am building for this compiler. So end all statement with a semicolon, that's not a hard requirement because it works most of the time anyway. And I will not talk about this because I will talk about them all further down. The first thing we do is we have to define variables, because this is a strongly typed thing, strongly typed language, if you will call it language. It's strongly typed. So, and I also can only use defined variables. That will eliminate spelling errors. If I have 100 equations and it produces the wrong answer, and I have a lot of alphanumerical text on the screen and something is wrong, it's very nice to get a warning if you have just misspelled the variable or something. So that will tell you that this is an undefined variable, and it will tell you where it is. See the other video about error messages. Anyway, so that's the first thing we do. I define a lot of variables and they would be named, that's not right, something like frog or mass, something that is easy to read. You know that as you are a programmer, but right now they are just named b for variables that are on the b side of the equation, and x for the variables we are solving for. And these numbers are the dimensions of the variable. So 11 is 1, 1, this means it's a scalar. This is 1, 2, so this means it has 1 row and 2 columns. 3 rows and 1 column. And this is a matrix, 3 rows, 3 columns. So these are defined, and I can only use those, and I can make something like this that reminds me of what the pre-computed variable means. But since this is a symbolic solver, a numerical solver is a completely different thing. They are also very useful, but this is not what this is. This is a symbolic solver. Anyway, this assignment is ignored and can be used as a comment to make it even easier to read. Okay, so this thing means this thing, and when these are all defined, I can define the x vector. So this is the x vector now. I have one scalar x variable, I have one 3 vector here and another 3 vector here. So this is how we define the x vector. Remember, we have this equation here. We want to produce A, we must give x and we must give b, and we must give a bunch of equations. So these are the equations I intend to show in this video. The first one is a scalar equation, and we have already seen scalar equation in the system of two equations that I started with. This is just, I'm showing the equations just one and one now, but in reality you would have a bunch of them, a system of them. So what we get is a matrix now that contains only a single value 1, because I have in position 3 here. If you look at the x vector up here, first position is x11t, second position is x13x1, like this. The first element of that is the second position in the matrix, and this is the third position in the matrix. And as you can see down here, I have this 1, meaning the third position in the matrix. So you can see I have a 1. This is the coefficient of the equation, or the x variable integration. And on the other side I have b11a, which is the b vector entry. And I have a too large x vector. The x vector must be as large as the number of equations I give for the matrix to be square and solvable. And up here you can see we get errors because we have mismatched sizes, and we will have those mismatches throughout this video, because I'm not fixing that right now. I'm just showing stuff. And so that's why these are mismatched. I have a too large x vector and too few equations, only one equation. I need 1, 2, 3, 4, 5, 6, 7 equations for this to be solvable. And I get warnings if I don't get that right. Anyway, another example of simple scalar equation. You can see the b vector and the coefficient of the equation. And the second one is a little bit more tricky to do by hand, because this is a vector equation, and this is the dot product between, no, this is multiplication. This is a scalar and this is a vector, right? So what will happen is that this equation is 3 equations, because this is a 3 vector, a 3 vector, and these are scalars. What I mean by that is that add the scalar to all elements of this vector. And now we have 3 equations, like I told you, and we have 2 x variables, x13x and x31y. So down here you see we have these 3 are the diagonal, or they are first position, second position and third position of the x13x variable. So they now form 3 equations, saying b11b is equal to b11a plus x31y first element. Alright, no. This is b11a times the first element of x13x. I'm sure you get the picture. You have some idea of what matrix systems, how they work. Otherwise you probably wouldn't be here. And if you're a hero. If you're here without knowing this is the first time, you are a hero for sure. And you can see the zeros are just duplicated, and the b11b are just duplicated to fit the size of the equation. You can do that because you're a scalar. And if you want to get rid of this 0 before the minus, you can delete this and it will know that, alright, I still have a b vector and I still have an x variable. so I know what to do. But you must have a b and an x, then you don't need a 0 here. And or you can also, let's see this. So when I did that, I got rid of the ugly 0 there. And I can also do this. I can put the equal sign on this side, and then I will have reversed the minus signs, negated the equation. So these are now positive and these are now all negative if I for some reason would see that, rather see that in the equation. And now we are back, we have the 0 and the minus, the positive here. Right, so that saves me from writing all three equations. If I have a vector equation, I only have to write the vector equation here once, which is less typing, and it is a lot easier to interpret if I had real variable names. So if I have vector equations, I immediately see that this crossed with this dotted with that means this and that, and it's easy to debug and it's easy to follow, so it's like readable code. The matrix on the other hand is just a bunches of ones and zeros and coefficients, and it is a mess to debug in that. Now I have sweet equations to read. What's the next equation I want to show? Scalar in vector equation. Vector multiplication with scalar. Yeah, just that I said in the previous equation. I can mix scalars and vectors and it knows what to do. Now the x vector is x11, meaning it's a scalar, and you can see it's down here. All the entries in the matrix are in the first position. In the other equation they were on a diagonal because they were a vector, but in this case it distributes the x11 in the correct way without me having to work for it. And this is division. You can have division by vectors, and in the matrix we have 1 divided by, meaning it is the x variable in the first position, x11t, divided by each element of the b13p vector. Since you have element 0, element 1, element 2 in the denominator here. Also works, no problema. Vector divided by vector also works. Now we have back the diagonal in the matrix, so we have different elements of the x variable here and different elements of the b variable, b13p0, b13p1, so they are divided element wise. And gradually building to some complexity, scalar divided with vector will produce 3 equations like I showed you before with multiplication and element wise multiplication. Alright, so we have, you can see this dot multiplication, dot asterisk, this is element wise multiplication. Will look like this, pretty much like the division, and I'm sure you know about element wise. It's called the Hadamard also in some circuits. And now we have the scalar product, a little bit more interesting. So if I can get the cursor back, Visual Studio eats the cursor ever so often, all the time actually, and I have to press F7 to get it back. Quite annoying. Now this is a 3 vector and this is a 3 vector, and this is a scalar product, which meaning that these vectors dotted with these vectors, it's called a dot product also, will produce a scalar. So this will be only one equation. Even though I have vectors here and vectors here, this will produce one equation like this. But you can see the equation, or the b vector side, looks rather complicated. So the dot product is the first element times the first element of the other vector plus the second element times the second element of the other vector, and you just add them together, and that's what you see. Oops, I destroyed the window. Here, element 0 times element 0 plus element 1 times element 1 plus. So this is now also written out automatically for me in the b vector. Would have been in the x vector were the equation slightly different. But I have scalar product, works fine. And even more interesting is the cross product. Cross product produces 3 equations, and now you see we have a lot of entries and it's getting more advanced. The cross product is another type of vector operator that you need all the time. Scalar product and cross product, that's the cornerstones of vector equations, at least the ones I am solving. And now the really cool thing is this. This is an equation with a scalar product here, or dot product, yeah. So this will produce only one equation. Down here you have the matrix only contains one equation with 3 entries for 3 x variables. First component of x, second component of x, third component of x. So this dot product contracts these vectors to only one equation. But this cross product had an x variable, an x vector variable in itself. So for this to be solvable, even though we have only one, or it will not be solvable in this case, I guess. But anyway, if we have 3 of these, we want to solve for all 3 of x. We need 2 more equations. But for this to work, anyway, I have to remember where the scalar came from. The scalar came from an x variable, and I want to solve for the x variables in the vector 1 through 3, first, second, third element. So that means when I do this cross product, I have another vector which contains the x element. But when I do this, I contract it down to a scalar. But to write the matrix, I still need to remember where did this scalar come from, even if I contracted to only one scalar. And that shows up in the matrix. You see, even though we have only one equation, we have coefficients, advanced coefficients even, for all 3 elements of the x vector. Remember, this is the first element of the x vector, second element of the x vector, and third element of the x vector. So in this case we have to remember where the x, how the x's relate to the scalar, even though we have 3 x's and only one scalar. That works, and that's pretty special for not numerical solver. I have forgotten the word. I just told you what it was called a second ago or a couple of minutes ago. Symbolic solver. You can't just make the number and forget about it. If you have a symbolic solver, you have more things to consider. A numerical solver can just do the operation in the right order and keep the number and forget about the rest. symbolic solver, you have to remember stuff, put things in data structures and do good things with them later to get the matrix. This is just a more advanced version of what I just told you. I have a cross product, I contract it like I did before, so now I have only one scalar. This is a scalar to the left of here, this is a vector. When I multiply them I will get a vector back, so now I have a vector again. And then I do another cross product with another vector, and all the time I have to remember, right, how does this relate to the x variables, all three of them? So how does the matrix look? How does the matrix look? So it looks like this. So things are getting a little bit more advanced now. But I am really glad I don't have to write this by hand anymore and keep track of everything and not make a mistake in any of these entries. I am happy about that. Other things we can do is binomials. So now we are doing the distributive rule, meaning, yes, you're probably above middle school, so you know about binomials. You have to multiply this by that and this by that and this by that, and in the end you get this. Not that hard, but still you have to remember stuff and do stuff to get the binomials to work in a symbolic solver, and we do. We also can do this with a dot product. The dot product is also a distributive, follows the distributive rule. So in the first equation we have scalars, now we have vectors, and this will become a dot product, so it will distribute over the parentheses. We only have one equation still because it is a dot product, and it will produce a scalar, but we have entries in all 6 x variables, x elements that we are solving for. We have 2 x variables here, 2 different x variables, 3 elements each. That's why we had 6 entries in that equation. Same thing, but with Hadamard, looks like this. Now we get 3 equations because we have element-wise multiplication. In the first one with the scalar product, we get only one equation. Here's the cross product. If I remember to uncomment it, looks like that. Distributive cross product, yes, looks like that. If I want to do division, I can do division like this, but I do not expand the denominator when it is parenthesized. So this will be considered just a scalar and be passed along just as it is, like this. So you will see I still divide by the same parentheses as it is. You can do vector division element by element as I showed before, but then you have to pre-compute the parentheses, which we probably would anyway. But just to show you how this works, and this is just more parentheses showing that it can handle not just binomial but even more parentheses like this. I have no x variable in this equation apparently, so all of the things came into the b vector. That's not a solvable equation, but it shows you that the multiplications work. Another version of more entries in parentheses. I'm not even showing this like that. Now something a little bit more interesting is parentheses in parentheses in parentheses. You can see we have a scalar here multiplied by something in parentheses, and this parenthesis goes all the way to here, so this will multiply to this, to this, to this, and then we have another parenthesis inside here, and we have one x variable here and another x variable nested far inside here. In the 1, 2, 3 third parenthesis we have an x variable, and it has to solve for both of these x variables, expand them out of the parentheses and get them into the equation. But this is a much nicer form, could be a much nicer form of this equation. So you may want to have it like this here to make it easy to read and debug and interpret. And if you do this, that didn't look so difficult, but anyway, I am also happy to not have to expand that by hand. Didn't look that impressive now, but when I programmed it, it felt more impressive because I had to do a lot of things to make that work. But the code here is pretty. I am very happy to be back in Visual Studio and C++ after an excursion into Xcode and Android Studio, which are okay, but this is a lot nicer to be in Visual Studio and C++. So what is the last equation I am about to show you? Because I will leave the other stuff for the error code video. This is operator order is preserved, obeying precedence. Yes, we have seen plus minus and multiplication are done in the right order. I haven't actually shown that, but they are. You have to do multiplication and division before you do addition and subtraction, you know that, and so does this compiler. But I had a version that actually did not obey this, because the cross product do not commute. So we have talked about the distributive rule, that it can handle the distributive rule, and now we have the commutative rule. X products do not commute, so you cannot change the order of the operands to a cross product. And this shows you that we must do this before that one in front of this. Oh, also this is distributive, because this cross product will go into this one and that one, and then at the end we have to do this one. I had a version where I collected all the one in the lower levels of the parens and I just multiplied them together, but that did not preserve order. This compiler version now does. So that works. We get these, and you can see that in the matrix these entries are the same. These are for the first x variable and these are for the second. So they are the same except for the minus sign, which is what happens when you flip the order of operations around the cross product. They're the same, but with a flip minus sign. So the commutative rule is also obeyed in this compiler. That's it. I will now start using this for my next project. So this is not just to learn, even though I'm happy to have started making something that I could build a compiler of, a bigger compiler of later. this was a I don't have that word. That word doesn't exist in English that I need. So small enough project that I can finish that I need for another project. Not a very eloquent ending to this video, but thank you for watching anyway. Hero.